Up to now, in this examination of RL circuits, you've seen that current is the same throughout, and that two primary types of relationships will always determine how an RL circuit will respond: phase relationships and Ohm's frequency relationships.
Let's continue examining RL circuits by seeing how the two different types of Ohm's values, resistance and reactance, are handled within the context of an RL circuit.
You know already that both resistance and reactance represent opposition to current flow. The total opposition in an RL circuit, which combines these two, is referred to as impedance. It is specified in ohms and is represented by the capital letter Z.
Let's use what you already know to derive a formula for total impedance in an RL circuit.
Impedance relationships to voltage and current follow Ohm's law. Because impedance is measured in ohms, Ohm's law for impedance can be stated as Z equals V divided by I.
But suppose that you don't know the total voltage and current for a given RL circuit.
What if the only known values are the resistance in ohms and the inductive reactance in ohms? Because these two values are 90 degrees out of phase, total impedance can be found by using phase relationships and the Pythagorean theorem.
Let's derive a formula for finding total impedance in an RL circuit in terms of the resistance and reactance, using what you've already learned.
Start with the form of the Pythagorean theorem that you are already familiar with. V sub t equals the square root of V sub r squared plus V sub l squared.
In algebra, you can divide each term of an equation by the same quantity without changing the equality.
Because current is the same throughout a series RL circuit, divide each term in the equation by I sub t. From this point in the derivation, let's simplify the right side of the equal sign by squaring both sides of the equation. This will eliminate the radical sign. Now, the right side of the equation reads V sub r squared plus V sub l squared divided by I sub t squared. Because there is a common denominator on the right side, rewrite it as V sub r squared divided by I sub t squared plus V sub l squared divided by I sub t squared. Now add parentheses on the right, indicating that each quantity is squared. Since the current is the same throughout a series circuit, the I sub t's on the right can be freely replaced with I sub r and I sub l respectively. If you look inside each pair of parentheses, you'll find some Ohm's law relationships that have already been presented. For example, on the left of the equal sign, V sub t divided by I sub t is Ohm's law for impedance. V sub r divided by I sub r is Ohm's law for resistance. V sub l divided by I sub l is Ohm's law for inductive reactance. Since you're not looking for impedance squared, but the value of impedance, take the square root of both sides of the equation. This will yield the formula for impedance in a series RL circuit. Z equals the square root of the quantity R squared plus X sub L squared. You can see how this is still based on the Pythagorean theorem. The phasor diagram would appear like this.
Let's apply the formula to calculate the impedance of an RL circuit.
This series RL circuit has a 3 kiloohm resistor and an inductor whose reactance at the applied frequency is 4 kiloohms. With the example value substituted, the formula reads the impedance, Z, equals the square root of the quantity 3 kiloohms squared plus 4 kiloohms squared. This results in the square root of 25 kiloohms squared, yielding 5 kiloohms for the circuit impedance.
Knowing the circuit impedance and the applied voltage, you can now determine the total current for this RL example.
Total current, I sub t, equals V divided by Z. The example RL circuit has an applied AC voltage of 30 volts and an impedance of 5 kiloohms. Let's determine what the total current will be. Substituting the values yields 30 volts divided by 5 kiloohms, or 30 divided by 5 times 10 to the third. which yields 6 times 10 to the minus third, or 6 milliamps for the total current.
Stop the program and complete activity number 2. When finished, continue watching the program.